Hello everyone, I am Ankush Pal. I am doing postdoctoral research under the supervision of Professor Arshad Kudroli in the Department of Physics at Clark University. Today I'm going to discuss about the drag anisotropy of a cylinder in fluid saturated granular beds. This work is supported by National Science Foundation. Granular particles are typically small solid particles which interact using the frictional forces. When these granular particles are immersed in a fluid, then viscous force also becomes important. Granular particles sediment in a liquid and then they form a static bed. This bed starts moving when the applied stress exceeds the yield stress, and this behavior looks like a Herschel-Buckley fluid. There are a couple of examples of granular particles settled in a liquid. The best example is the sea floor. Apart from that, we have examples of slurry and bubble tea. Initially, it was found that the drag force by an intruder is constant at low velocities, but it was found to increase linearly with depth. Later, from our group, it was found that the drag force increases rapidly with speed for both the case of granular hydrogels and glass beads. Now we discuss about the drag anisotropy in sediments. Drag anisotropy is the ratio of the perpendicular drag to the parallel drag. In case of a rod moving through viscous fluids, this drag anisotropy was found to be 2. In case of dry granular particles, the drag anisotropy was as high as 10. Then in our group, it was found that the drag anisotropy in granular hydrogels immersed in water, the anisotropy becomes 5 to 7. So there is a lack of systematic study of drag anisotropy, though they are important in determining the speed of organisms and robots burrowing through the sediments. So our first objective became to study the effect of the aspect ratio of cylinder on drag anisotropy. Then we are interested to investigate the contribution of frontal and side lobe of the cylinder on drag anisotropy. We were also wanted to know that the effect of speed on the drag anisotropy. And finally, we changed the granular particles, and then we wanted to know the effect of the material properties on the drag anisotropy. So here is our experimental setup. The intruder is of cylindrical shape, which is attached with the force sensor using a thin rod. The force sensor is further attached to a translation stage, which can move both forward direction and reverse direction. So if intruder axis is oriented in such a way that it becomes parallel to the velocity or motion of the intruder, then we say it as parallel drag. But if the orientation of the intruder is perpendicular to the direction of motion, then we say it as a perpendicular drag. We have used two different types of granular particles here. One is granular hydrogel and then is polystyrene beds. The intruder aspect ratio was varied from 5 to 40. The lowest velocity for intruder was 0.05 millimeters per second, and the highest velocity we have used 8 millimeter per second. So first, the raw data is the torque after the intruder moves through the granular bed. The intruder is attached with the rod. So the torque which we receive for the intruder, that is actually a torque for both intruder and rod. So we also measured the torque of the rod only without the intruder. And once you subtract from the torque of both intruder and rod with the torque of rod only, and then you divide that by the rod length, you will end up in getting the drag force for the intruder in the granular material. That drag force was then converted to the effective friction. Effective friction is the ratio of the drag force to the normal force acting of the intruder. So we have measured the drag force both in parallel and perpendicular direction. So we have effective friction both in parallel and perpendicular direction. The effective friction is actually the ratio of the drag force and the normal force acting on the intruder. So once you divide the drag force by the overburden pressure due to the granular particles on top of the intruder at a certain depth, and then you divide also by the area of the intruder. So we found that this effective friction converges to a constant value at low velocity, and then it starts increasing slowly at the lower velocity regime, and then it increases rapidly at the higher velocity. This was found both for perpendicular and parallel drag. Then we calculated the drag anisotropy, which is the ratio of perpendicular drag to the parallel drag. For a particular aspect ratio, we found that there is no impact of the variation of velocity on the drag anisotropy. So the low velocity and the high velocity, we found the drag anisotropy is almost comparable. So we can say that drag anisotropy is constant irrespective of the velocity which we have studied. But we found that this drag anisotropy changes with the aspect ratio. The drag anisotropy found to be increasing at the aspect ratio of the cylinder increases. Further, we wanted to know the effect of the front and side lobe of the cylinder on drag. So here is the intruder oriented parallel direction with the motion. So you can imagine the intruder frontal lobe as a thin slice having the same diameter of the intruder, and this slice length is very small. So effectively we can say that contribution is for only frontal lobe. So we measured the drag force for this slice in the parallel direction. Similarly, we also found the contribution of the side lobe in case of perpendicular direction. So side lobe also, you can imagine it as a very thin slice having the diameter as the diameter of the cylinder, and the length is very small. So here also you find the torque of that thin slice in perpendicular direction. Then both these slice torque have been deducted from the original parallel torque and the perpendicular torque, and both of these subtracted value then gives us the subtracted drag anisotropy. So interestingly, it was found that after the subtraction of this lobe effect, the drag anisotropy increases. And then this increase becomes less dominant as the aspect ratio of the cylinder increases. So we can say that as the diameter becomes lower compared to the length, then this significance of the subtraction of the frontal and side lobe becomes less significant. Now we have measured again the drag force with polystyrene particles, and then we converted that drag force to the effective friction. So we found that here also the effective friction almost converges to a certain value, or all irrespective of all the aspect ratio of the intruder we have studied. Then effective friction increases slowly at low velocity, and finally it increases rapidly at higher velocity. We then further calculated the drag anisotropy in polystyrene particles. Here also we found that there is no variation of drag anisotropy across the velocity we have studied. So drag anisotropy remains constant with the velocity. However, here we don't see much strong effect of the aspect ratio of the intruder on the drag anisotropy. However, it needs further study for us to determine exactly that the effect of the aspect ratio on the drag anisotropy for polystyrene particles. As we saw for hydrogel particles, here also in polystyrene particles, we have seen that drag anisotropy increases as we subtract the frontal and side lobe of the cylinder. So now we come to the conclusion. We have found that the effective friction which have been derived from the drag force are comparable or almost close to each other at the lowest velocity, irrespective of all the intruder aspect ratios. Drag anisotropy increases as aspect ratio increases for hydrogel particles. However, the behavior with the polystyrene particle needs further study. Drag anisotropy depends on the nature of the particles. Like for polystyrene particles, we have found drag anisotropy a certain value, and then for hydrogel particles, we have found drag anisotropy to be different. So it depends on the nature of the particles, whether it's a soft hydrogel or a hard polystyrene particles. We have found a strong contribution of front and side lobe of the cylinder on the drag force. And once you remove this contribution of front and side lobe from the cylinder, you found that drag anisotropy increases. So overall, we can say that drag anisotropy of a cylinder in sedimented granular bed depends on the dimension of the cylinder as well as on the properties of the granular particles. Thank you.